Welcome, fellow chemists. For years, I've used this PhET simulation with my students when we get to the gas laws. It does a really good job at demonstrating the simplest three you may remember. For example, we can discover the relationship between volume and pressure, but before I do, I'm going to turn the fluctuations on the pressure gauge off and make the box as small as possible. The width of the box is 5 nanometers, and the pressure is currently 58.4 atmospheres. I will record the pressure for every 1 nanometer increase in width. The inverse relationship is obvious because by the time I'm done, we can see the pressure has decreased from its original value to 19.5. I can take the data, plug it into a spreadsheet, and see what this inverse relationship looks like in graph form. If we are ambitious, we can use this information to derive the actual equation for Boyle's law. I'm just going to put it on the screen. But wait a minute, Boyle's law doesn't have width, it has volume. So what is the volume of the box? Back in the simulation at default width, we have no way of knowing the height or depth of the box. I would say, at least at first glance, it appears to be a square, which means the height is about 10 nanometers. While it might be a good guesstimate, I actually have to measure it. Luckily, the Chrome extension Pixel Screen Ruler works perfectly. It was maybe the third or fourth one I tried, so though I may never need it again, I'll recommend it for the fact it actually did what I wanted it to do. Anyway, we can see the width of the box is 440 pixels, but the height is only 385. With a ratio of 44 pixels per nanometer, the resulting height of the box is 8.75 nanometers. 2 dimensions down, 1 to go, and I can get it if I use the simulation to find volume. Let's consider what I know. Pressure, temperature, width, height, and the number of particles. That information is quite close to what is required to use the ideal gas law, PV equals nRT. R is the gas constant, though N is not the number of particles but the number of moles. I know I can use moles to get the number of particles, but since I know there are 50 particles in the box, I want to use that number if possible. Luckily, there is another version of the law, PV equals nKT. This time, N is the number of particles exactly, and K is Boltzmann's constant. We can calculate K by taking the R value, 0.0821 since we are using atmospheres, and dividing it by Avogadro's number. For this calculation, K is 1.36 times 10 to the negative 25, but that's using liters as the volume. Since the box dimensions are in nanometers, I need to convert liters to cubic nanometers. There are 10 to the 24 cubic nanometers per liter, which results in a K of 0.136. Now that all of the variables have been settled, I can finally determine the depth of the box. My spreadsheet is already prepared. Depth is calculated by multiplying the number of particles, Boltzmann's constant, and temperature, then dividing by pressure, width, and height. I already know what everything is going to be except pressure. So looking back at the simulation, I see the pressure is 5.8 atmospheres. Putting that into the calculator, the depth of the box turns out to be about 4 nanometers. I have no idea how reasonable this value is, but it seems neat and clean, which could make a lot of sense from an it needs to be easy to program perspective. For the next 2 tests, I can copy everything but change the widths to 5 and 15 respectively, and of course remove pressure. Shrinking the width down to 5 nanometers increases the pressure to 11.7 atmospheres. This results in a depth of approximately 4 nanometers again. My confidence in my work is growing, but we all know science is settled if we can do it 3 times. Maximizing the width of the box results in a pressure of 3.9 atmospheres. Placing that into the calculator gives, once again, about 4 nanometers. Well, that's 3 calculations all giving the same result, so it's settled. Except I'm not satisfied. It's possible I made some error that for reasons isn't impacting this particular calculation. So I'm going to run a few more tests, first calculating the number of particles. Once again, I will use the default, smallest and largest box sizes with a depth of 4 nanometers. The temperature will be 300 Kelvin, and the K value is 0.136. Calculating the particles involves multiplying pressure by all 3 dimensions and dividing by K and temperature. Now, before you worry about any funny business, I can hide the number of particles in the simulation and use the pump to add a random number of particles into the box. The pressure inside the default box is 27 atmospheres, and my calculator estimates there are 232 particles in the box. It turns out it is actually 231, which is more or less exact. Perhaps I got lucky, so let's look at the smallest box. Here goes some blue particles, and the pressure is 136.9 atmospheres. The particle estimate is 587, and the actual is 586, which is once again spot on. Alright, for the largest box I'm going to switch to the lighter red particles. It shouldn't make a difference, but let's see. With a pressure of 57.1 atmospheres, the number of particles is estimated to be 735, and turns out is 733. It certainly seems as if I've done it right, but getting consistent results in 3 successive tests for 2 different variables is one thing. I want a hat trick of hat tricks. I want this to be different than the other calculations, so I'm going to put in 100 heavy particles. I'm going to hold the pressure constant, but this selection allows me to adjust the temperature, which will then affect the volume accordingly. What I'm ultimately interested in is the width of the box. I can calculate it by multiplying the number of particles by K and temperature and dividing by pressure, height, and depth. But I don't have the temperature yet, so I'm going to increase the temperature a bit, and now it's 382 Kelvin. This predicts a width of 12.7 nanometers, and the result is perfect. Now I will reset, maximize the size of the box, then add 200 light particles. This time I will drop the temperature to 145 Kelvin. The calculated width is 7.2 nanometers, and once again it's identical to the simulation. So far I've used a version of the ideal gas law that even I was not familiar with before I started doing this. So to finish off this hat trick, I'd like to use the more familiar one, PV equals nRT, and I'm going to use it to calculate the pressure inside the box. This whole journey started because I did not know the volume of the box, and now I get to finally calculate it. 8.75 by 4 by 10 nanometers results in a volume of 350 cubic nanometers, or 3.5 times 10 to the negative 22 liters. The expected temperature is 300 Kelvin, and R is 0.0821. I will put 1,000 particles into the box, which is 1.66 times 10 to the negative 21 moles of gas. All of this predicts a pressure of 116.9 atmospheres. Let's add 1,000 particles to the simulation and, I hope you're throwing your hats, the pressure is 116.8. So after years of using this simulation without questioning it, I can say the width is between 5 and 15 nanometers, has a height of 8.75 nanometers, and is 4 nanometers deep. The volume ranges from 175 to 525 cubic nanometers. Does the simulation have all of those dimensions or the starting volume specified in the code, or does it keep track of the information in another manner? I have no idea, but in any event, I'm glad I went and calculated it, if for nothing else than the exercise. If you happen to know, please leave a comment as I'm genuinely curious. The origin story for this video was an activity I made for my students after I realized I did not know the volume of the box. As I was making this video though, I realized how much I can improve the original lesson as my approach here is much simpler. If you're a teacher who stumbled across this video and would like the newly updated packet, I will put a link to it in the description when it's ready. However, it's currently July 1st as I record this, and I'm not in a doing schoolwork kind of mode. In the meantime, thank you very much for watching.